Hello, this is Professor Werwath. I'm here to finish up the case for green chemistry. This will be part two of the discussion. Where we left off was the section on spills and disasters. I'm going to go through a series of those. We'll finish up with what is green chemistry and a video from the state of Michigan on the green chemistry definition from their perspective. So some of the disasters we've seen as a result of the chemical industry includes the Bhopal gas tragedy from 1984. Effectively, what happened here is 500,000 people were exposed to methyl isocyanate, MIC gas. The highly toxic substance made its way into and around the small towns located near the plant. Estimates vary. I've seen estimates as high as 8,000. Wikipedia pegged it at something like 2,250. In 2008, the government had paid compensation to over 3,700 victims that were killed in the gas release and to 574,000 injured victims. So major issue. You can see the photograph in the upper right. Obviously, a lot of safety issues here, but this was fundamentally a pesticide plant, okay? A pesticide plant in India that with the accident caused tremendous damage. Additional examples here, these are going to be mostly US centered examples. So Woodbine, Georgia, a chemical plant was set on fire and later exploded on February 3rd, 1971. The plant was operated by Thiokol Chemical. There was 35 buildings in the facility, stretched over 7,400 acres. The fire was mostly limited to one building, M132. The results, first of all, the fires were started where an ignition chemical was added to other chemicals. While other small fires were not rare, this one quickly proved to be different. Within minutes, all 80 workers were evacuated. The fire then reached the plant storage room, which caused the blast. So the results were catastrophic. 24 people died during the explosion or immediately thereafter, 5 dying later from related injuries, and 50 others suffering catastrophic and life-changing injuries. So obviously, tremendous impact there. The Henderson rocket fuel plant explosion, 1988, Henderson, Nevada. Ammonium percolate plant explosion, registered 3.5 on the Richter scale, was felt 600 miles away. The plant, decimated $100 million plant, was gone, right? And it made rocket fuel for the US space shuttle program, right? Luckily, at the time, the program was on hold. Unluckily, of course, 2 people got killed, 372 people injured, $100 million worth of damage. Phillips disaster, right? This is a Houston Chemical Complex facility, Pasadena, Texas. HDPE was being produced there. The accident occurred during routine maintenance. 85,000 pounds of flammable gases were released instantly. The gas traveled through the plant. Within 2 minutes, came into contact with ignition source and exploded. The fire and explosions killed 23 people, 315 were injured. The Sterlington plant, right? This was a plant owned by Angus Chemical, based in Northbrook, Illinois, 7 miles from Northwestern, right? Operated by IMC for Fertilizer in Sterlington, Louisiana, suffered from a series of blasts. Severe injuries were caused, and approximately 600 residents were evacuated. Severe damage to buildings. Windows were blown out, siding ripped from homes. The business district was hit very hard. Small fire was reported in the plant, and blasts occurred about 30 seconds later, which could be heard 8 miles away. The blast killed 8 of the workers at the plant, injuring another 120. The West Fertilizer plant explosion, West County, Texas, killed 15 people, injuring at least 200 more, damaging 350 homes. The explosion occurred after a fire broke out in the plant caused by a faulty golf cart and electrical malfunction. 270 tons of ammonium nitrate were being manufactured on site and ignited, right? So the blast blew out windows miles away, registered as an earthquake. Crater 10 feet deep was left behind and nearly 100 feet wide. 15 people were killed, and 200 others were injured in this explosion. So you can see that, I could have done a very similar narrative on oil facilities and oil plants, petrochemical facilities. I chose not to. That list would have been even longer and more environmentally atrocious in terms of the long-term impact on the ecosystem. So you can see between the chemical industry and the petroleum industry, we've got a lot of history, I guess, of problems and not enough solutions. So one solution is green chemistry. Green chemistry is the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances, okay? Behind these great words are 12 fundamental principles, and I'm going to go through them very briefly here. But the first one, of course, is prevention, right? And almost all of these principles are revolving around waste, right? How we deal with waste. So you can think of it almost like Toyota lean manufacturing applied to chemistry, right? It's better to prevent waste than to treat or clean up waste after it's been created, right? The atom economy is a second principle. Synthetic methods should be designed to maximize the incorporation of all materials used in the process into the final product. Again, eliminating waste, right? Or reducing waste. Less hazardous chemical syntheses wherever practicable. Synthetic methods should be designed to use and generate substances that possess little or no toxicity to human health and the environment, right? Makes sense. Designing safer chemicals. Chemical products should be designed to affect their desired function while minimizing their toxicity. Safer solvents. The use of auxiliary substances such as solvents and separation agents should be made unnecessary wherever possible and innocuous when necessary. When it's being used, make it harmless. Design for energy efficiency. So part of the whole issue with chemistry as we've known it is in Haber-Bosch in particular, is the tremendous amount of energy being used and in most cases wasted, right? Energy requirements of chemical processes should be recognized for their environmental and economic impacts and should be minimized. Synthetic methods should be conducted at ambient temperature and pressure. So those are the first 6 principles. The next 6, use of renewable feedstocks, right? So raw materials should be renewable rather than depleting. Makes sense. Reduce derivatives, unnecessary derivatization, use of blocking groups and protection, deep protection, temporary modification of physical chemical process should be minimized or avoided if possible. Such steps typically require additional reagents and generate more waste. So there's a very consistent theme here. Reduce or eliminate waste. Catalysis. Catalytic reagents are superior to stoichiometric reagents. Design for degradation. Chemical products should be designed so that at the end of their function, they break down into innocuous degradation products and do not persist, unlike the forever chemicals, the PFASs of the world from the previous video, right? This is an actual targeting of that particular issue, right? Real-time analysis for pollution prevention. Analytical methodologies need to be further developed to allow for real-time in-process monitoring and control prior to the formation of hazardous substances. Inherently safer chemistry for accident prevention. Substances in the form of a substance used in a chemical process should be chosen to minimize the potential for chemical accidents, including releases, explosions, and fires. So all those examples I gave before, this is an actual targeting of that. So focus on waste, focus on energy use and misuse, safety, right, and persistence in the environment, right? Those are the key foundational principles within these 12 principles. This is effectively what's driving those 12 principles. I want to share with you now a video. And this video comes to us from the EGLE of Michigan. This is effectively the Michigan State Environmental Group. Let's watch.
Green chemistry to me means designing the materials and the chemicals that we will use in the future that are better for human health, that are better for our environment as a whole, and that will help us to design an efficient planet where we utilize everything in sort of a circular way so that everyone's life will be better.
Green chemistry is a fundamental approach to developing chemical products in a very safe, environmentally friendly way. Examples of that would be to make let's say, a drug product without using ingredients that are toxic, constituents that are toxic, or solvents that are toxic. And green engineering, I think, refers more specifically to the methods employed
So we tend to spend a lot of time, thinking about ways to assess the hazard or risk of a chemical, and we spend a lot of our energies there. But I think the true potential, the true value of green chemistry is about innovation. It gives us, again, the conceptual framework to start thinking about what is it that we want the material to do, and how can we achieve that function that we want, but in a way that doesn't have those impacts. I think it refocuses us on where we should be applying our energies and our intellect in the design of the actual chemicals and products.
So to wrap up, there's two concepts that came out of that video that I want to emphasize. We will be covering at least one of them later in the course. This idea of the circular economy, right, which is not just dealing with the pushing of product into the market, but also how that product gets retired and recovered, recycled and reused. So that whole circular economy has got to be part of product design and process design from the very beginning. So that concept we will not cover as much as this next concept, which is called life cycle analysis, right? What is the life cycle impact of any new product or process? Understanding it from start to finish, womb to tomb, answering the question as an example, right? Is lithium ion batteries in electric vehicles a better or less impactful technology than internal combustion engines, right? Looking at it from start to finish in a holistic way. So these are the topics we will be covering later in the class. So hopefully you found that useful. We'll be glad to talk about this in more detail in class.